Sometimes it's really important for us to find out where we have turning points in functions and whether those points actually happen to be maximums or minimums for the function. There is a simple test which we'll go through, and it allows you to determine whether you actually have a maximum or minimum for the function at that point. First thing we need to understand is that turning points for any function, not just quadratics, turning points occur when dy dx equals 0. So for instance, we've only done parabolas, but you can have functions that look like that. All right, so here we have a turning point, and if I drew a tangent at that point, it would be parallel to the x-axis, so we'd have a gradient of 0. Same with that one there, same with that one there, and the same with that one there. All right, so even without drawing the function, we can actually determine whether the turning point is a maximum being something like this when it goes up and turns around and comes back down again, or it is one of these. This is what we call a local minimum. So we've got a local maximum, minimum, maximum, minimum. But that's if we knew how to graph it. But if we get a graph that we don't know how to graph, we can still work out the nature of turning points. So turning points occur when dy dx is equal to 0. So if we can find dy dx, we can actually find out where the turning points are. The other thing is that we can use what's called the first derivative test. Now we've found the derivative, we've got dy dx. If we look, say, at this area, and we'll just look at that one here. So we want to find out, we didn't know what the graph looks like, but we've actually found out that at this x value, we've got dy dx is equal to 0. And we want to know, we don't know because we haven't drawn this graph, but we don't know whether the graph's coming down like that or it's going up there. But what we can do is, if we just substitute in an x value just a bit less than where dy dx is equal to 0, and put that in dy dx, and if we do get a positive there, and we do a value of x just on the other side of where dy dx is 0, and we get a negative gradient there, then if dy dx goes from positive to 0 to negative, so it's gone from a positive value on this side to 0 down to a negative, therefore we must have a maximum for the function. Now instead of writing it like that, you can go that, and that sort of shows you that you're going up and coming down. If dy dx, however, goes from a negative, so to say 0, well, let's just write it as, instead of using the lines, we'll go from a negative to 0 to positive. In other words, we're going like that, and positive like that, then we must have a minimum for the function. So once again, if we didn't know what this graph looked like, and we found out that dy dx is 0 at this point out here, and then we just substitute an x value in dy dx just on the left hand side here, and we got a negative gradient, then we'd have a 0 gradient here because that's how we found that point, and then we've got a positive gradient there, therefore you must have a minimum for the function. This is f of x, not f dash of x there. All right, so let's put that into practice. So find the turning point and its nature. Now its nature just means whether it's a maximum or minimum. Find the turning point and its nature for the function y equals 12 minus 4x minus x squared. Okay, so we don't know what that graph looks like, 12 minus 4x minus x squared. We want to know what the turning point. So turning points, as we said, are when dy dx equals 0. Just remember that. All functions, doesn't matter whether they're quadratics or sine graph, cos graph, doesn't matter. Turning points occur when dy dx equals 0. So if we find dy dx here, derivative of a constant 0, so that'll be negative 4 minus 2x. So 0 equals, so we're going to find out where this graph has a turning point, equals minus 4 minus 2x. Take the negative 2x to the other side and you get 2x equals negative 4, x equals negative 2. So at x equals negative 2 we've got 0 gradient. So we have a turning point there. We don't know whether that's a minimum or a maximum. So we're going to do the first derivative test. So I suggest you draw up a table. And we have x equals and dy dx. And we're going to do, we know at x equals negative 2 that dy dx is equal to 0. You choose a value of x just a little bit less than negative 2. So let's go negative 1. And then you choose one on the other side of negative 2, negative 1, negative 3, and this will be negative 1 over here. Okay, so negative 3 is just less than negative 2. Okay, so put negative 3 into dy dx. So we want to find out what dy dx is equal to when x is equal to negative 3. So it'll be negative 4, take 2 times negative 3. That's equal to 6. Take 4 is equal to 2. When x is equal to negative 1, we substitute negative 1 into dy dx, and you get negative 4 plus 2, which will be equal to negative 2. So negative 4 minus 2 times negative 1. Negative 2 times negative 1 is positive 2, minus 4 is negative 2. So my gradient has gone from a positive 2, positive gradients look like that, it's gone to 0, and then it's gone to a negative gradient. So therefore, using this as the first derivative test, therefore a maximum, this must be a maximum up here, maximum occurs at x equals negative 2. And if you wanted to know what the maximum was when x equals negative 2, what is the value of the function? Y equals 12 minus 4 times negative 2. We are substituting back in the original equation. 12 minus 4 times negative 2 minus negative 2 squared. So it'll be 12 plus 8 minus, now negative 2 squared is positive 4, so minus 4. And that will be equal to 16, I think, is it? So the value of the function is equal to 16 when x is equal to negative 2. And indeed it is a maximum then. All right, now, once again, first derivative test, if we knew it was negative 2 and this went from negative to 0 to positive, we would have that going on and you'd know you'd got a minimum at negative 2. But in this case, it went like that. So we know we've got a maximum.